Again, welcome to Discrete Mathematics, CS 113, also called Mathematical Structure for Computer Science. In these lectures, we're going to discuss about propositional equivalency. Our main objective is to go through what is tautologies, what is contradictions, what is contingencies. Also, we're going to discuss about logical equivalency, how do we find it, and normal forms, and also propositional satisfiability. So first we start with the tautologies. Here we say a tautology is a proposition which is always true. So an example is P or not P. Again, here I'm going to use the term disjunction will be or, conjunction will be N. So we can say that from this example, if P is 1, then not P is 0. 1 means true, 0 means false. Or if P is true and not P is false, then P or not P always will be the same true. The answer will always be true because true or false is true. False or true is also true. So this is what we mean by an expression or proposition is tautology. Tautology means is always true. And also we have the term contradiction. Contradiction means it's always false, the expression. So here we say a contradiction is a proposition which is always false. So a very simple example, P and not P, always false. Because we only get true with N operator, which is conjunction, N operator, if both conditions are true. But P and not P, always one will be true, one will be false. So this is always contradiction, always false. False means contradiction. And then tautology means always true. And also we have what we call the contingency. Contingency means the proposition is not tautology or is not contradiction. So it's neither contradiction and tautology. So we use this truth table to explain. Again, in this truth table, we have P and not P, because in our two examples, we are using only P variable. So if P is true, not P is false. If P is false, not P is true. Now, if I have only one variable, then the number of combination I may have will be only 2, either true or false. And as we said earlier, always when you are constructing a truth table, the number of rows or the number of possible combination depends on the number of variables or input you have. So always the base is 2 because it's binary. Logical, Boolean, or binary is always 2, either true or false. So the number of input will be our exponent, raised to the power. So here the number of variable or input is 1. So 2 to the power 1 is 2. So the possible number of rows will be 2, true or false. Now if I have 2 variables, then 2 to the power 2 will be 4. So possible combination will be 4. That is true, true, false, false, true, false, or false, true. So it will be 4 rows. So let's check with this example. We have only one P variable, so 2 rows, true or false. So if P is true, then not P is false. If P is false, not P is true. So now we want to check if P or not P is always true. So here we say P or not P is true because all means only one condition have to be true, or one input or variable have to be true. So here P is true, so our output is true. Here not P is true, so our output also is true. Then with the contradiction, we use N operator. So P and not P always false, because we said the N operator, we only get true when all the inputs are true. So here we can see the false and false. True, false is false. False, true is still false. So again, tautology means our expression is always positive or always true or always one. Sometimes we use one, positive or true. Then contradiction means our final expression is always false or negative or zero. Contingency means the proposition is neither a tautology nor a contradiction. So such as P, if I have only P by itself, P is neither tautology or contradiction. We can't say it's true or false. We can't determine. So what is a logical equivalent? A logical equivalent means if we have two expressions that they are logically the same, then we say they are logically equivalent. What we mean by the logically the same is their logical output is the same. So we can have two expressions, different expressions using different operators, even using maybe different variables, but they are logically equivalent, which means the output of those two expressions are always the same. Normally, we can use a truth table to determine if two logical expressions are equivalent. So here, we said two compound propositions, P and Q, are logical equivalent if P biconditional Q. The double arrow means biconditional, which means if and only if P then Q. And this is again tautology. Then we write this also as, we can use this double arrow with double line, or we can use the straight three lines, which means the same thing by conditional. So two compound proposition P and Q, they are equivalent if and only if, which is by conditional, the columns in the truth table giving their true values agree or they are the same. So normally we can again use the truth table to determine if different two logical operations are the same or they are equivalent. We can also use the Boolean algebra by using the Boolean logical. Actually, we will see that example soon, using the logical rules to solve the two expressions. So here we can say an example that not P or Q is the same as P in price to Q. So here we can see we are using two different operators. We are using or and also in price. So not P or Q is the same as P in price to Q. The fastest way to check this is using the truth table. So we look at how many inputs we have or how many variables we have. We have P and Q. So the possible combination, again, the base is 2 always. The number of input is 2. So our exponent will be 2. So 2 raised to the power 2 is 4. So the possible combination of two variables is 4. And that's why we have 4 rows here. So we get true, 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 false, false, true, false, false. Now, since we have a not P in our expression, we can come up with a third column, not P. So if P is true, not P is false, true, false, false, true, false, true. Then let's check our first expression, not P or Q. So not P is false, but Q is true, so the answer will be true. Again, all means only if all the expressions are false, then we get false. If I have 3 inputs, or even 10 inputs, or 10 variables, and 9 of them are false, but 1 is true, the output also will be true. So that's why here we have true. But in the next section, we have both false, false, false. Q is false, not P is also false, so our output is false. Then we also have true, true is true. False, true also is true. Now let's check the P in price to Q. We said P in price to Q is only false if the left side, which now is P, is true, but the Q, the right side, is false. That's when we get false. Apart from that, the rest are true. So the first we have true, true. So our output is true. Second, we have true, false. Again, the left side is true and the right side is false, so the output will be false. Then if we have the left side false, but the right side is true, the output will be true. Then if both of them are false, the output still will be true. So by looking at this, the fourth and fifth columns, we see that, oh, the output are the same. So if the output are the same, then we can come to a conclusion that not P or Q is the same as or equivalent to P implies to Q. So here we use the truth table to prove it. So next we should know what is a DeMorgans law. We are going to cover this more detail when we cover Boolean algebra and logic circuits. But for now, we should know some few concepts. DeMorgans law normally deal with negation or implement, invert, negation or invert, or complement. Again, most textbooks, in this our textbook, we are using negate. Negate is the same as invert or complement. What we mean by this is that complement of false is true. Negate of false is true. Invert of false is true. And the opposite also. True is false, false is true. So with DeMorgans theory, if we have example P and Q or invert, the invert is outside the parentheses, which means everything in the parentheses, they are inverted or negate. So if P and Q are all negate, we can separate each term and operator by saying that it's the same as saying not P, invert of N will be or, then invert of Q will be not Q. So this is this equivalent. Again, we are using the 3 dashes here, which means equivalent or the same. So P and Q or invert is the same as P invert. Then instead of or, we have N. The invert of N is or. The invert of or is N. So this will be invert of N, we get or. The invert of Q will be not Q, or invert of Q. Then if we have P and Q or invert is the same as P invert, N invert will give me, or invert will give me N invert, then Q invert. So always N invert is the same as or invert is the same as N. So here we have the first, we have P and Q or invert. So the answer will be invert of P, invert of N will be or, invert of Q will be Q invert. Then here we have or, so or invert will be N invert. Then P is P invert, Q is Q invert. Now we can use the truth table also to determine if DeMorgan rules here. This is the second DeMorgan's law, if it's correct or not. So here we have two variables, P and Q. So again, the possible combination is 4, TT, TF, FT, FF, 4 rows. We have not P, so I include not P in the third column. So P is true, not P is false. P is true again, not P is false. P is false, not P is true. P is false, not P is true. Then we also have not Q in the expression, so let's have not Q as our fourth column. So Q is true, false, Q is false, true, Q is true, false, not Q, false is true. Now we have P or Q. We are checking the second expression. So let's see what is P or Q. True, true means true. True, false means true. False, true means it's true. Again, the only time we will get false for P or Q is when both P and Q are false. Otherwise, everything is true. So if I'm looking for not P or Q, then I'm going to invert or negate P or Q. So P or Q is true, so it will be false. True again, false. True again, false. Then false, then true. Now we have not P and not Q. We said they are the same. So let's check the not P and not Q if it's the same as P or Q or not. So here we have false, because false is false. False, true, we are using N, so it will be false. True, false, we still using N, so it will be false. And the only time we get true with N is if both expressions are true. So the last section, not P is true, not Q is true. So not P and not Q will be true. So when we look, okay, the last two columns are the same. So here we say that the rule is correct, the DeMorgans second rule, because the output of P or Q not or invert is the same as not invert P and not invert Q. So these are the logical equivalences rules that we should know, and this will help us to solve the expressions. For example, they may give us one expression, a complex expression, they may say we should prove if it is the same as a second expression, which maybe to be simple. So here, instead of using the truth table, I can use these identities or these laws to solve it. And we may see this more when we cover the Boolean algebra. So identity law means if I have P and true or false, always my answer will be P. So the first example, identity law said, P and T is always P, but P and F is not always P. It may depends on the value. So P, here if P is true, true and true is true. If P is false, false and true is still what? False. So P will determine is the answer. The same thing applies to or. If I'm using or, then I'll use false, because or if I use true, if it's P is false or true, it will still give me true, it won't give me false. So here I have to use false. P or false always will give me P, because if P is true, my answer will be true. If P is false, false or false, the answer will be false. True and false, the answer will be true. So P value will determine. And that's why it's called identity laws. The P value always will be the answer. The true or false doesn't matter. We also have the domination laws. In the domination laws, the same concept. This time, instead of P to be our answer, the constant T or F will be the answer. So for example, if I have a P or T, the answer will always be T. Why? Because if P is true, the answer will be T. If P is false, the answer also will be T. It's not like previously, if P is false, the answer will be false. If P is true, the answer will still be true for N or O. And the same thing applies. If I have P or false, the answer will always be false, because if P is true, the answer will be false. If P is false, the answer also will be false. Then let's go to the third. The third law said that if we have the same expression, the answer will take only one. So true, true will give me true. False, false will give me false. So that's what we have here. P or P, it's always P. The same thing, P and P is always P. So if P is true, true and true is true. If P is false, false and false is always false. Then also we have the negation double law. If you have two negation, all you need to do is cancel the two. So negate P will be P, because the negate cancel negate. So the answer remains P. Then that's double negation law. Then we have negation laws. Now P and not P will always be true, because if P, not N, is all. N will always be false, because if P is true, not P will be false. So true or false is always true. False or true is always true, is all. But with N, it will be false. So true and false is false. False and true is always false. So with the or again to always be true. And here remember we have only one variable, either P and not P. So if P is true, then not P is false. If P is false, then not P is true. And the binary only these two input, true or false. We also have the commutative loss. Commutative loss is the same as arithmetic commutative. And the position 2 times 3 is the same as 3 times 2. 1 plus 2 is the same as 2 plus 1. So this is commutative loss. P or Q is the same as Q or P. P and Q is the same as Q and P. Then we also have the associative loss, same as arithmetic. The only thing is that here we have 2 items in the parentheses. When we change the item in the parentheses, it's the same operator, so they are the same. You can see the operators are NN. The down one, everything is all throughout. So changing the position of the variable will not affect the solution. Then in distributive loss, in arithmetic means take one expression, multiply by everything inside the parentheses. The same concept here. I will take P multiplied by Q, then I'll take P multiplied by R. So we get P or Q and P or R. Or we get P and Q or P and R. Absorption means to absorb something. So if I have the same variable P or P and Q in the parentheses, the answer will be P. Or if I have P and P or Q in the parentheses, the answer will be P. So absorption is very good for reducing a long expression. Then we have more logical equivalences. For example, the previous ones is very common to understand. We're going to use them mostly like in Boolean algebra most of the time. But also there are some complicated ones here. So P implies to Q is the same as not P or or Q. Actually, we did this example somewhere in this lecture, some in the earlier beginning, in the beginning of this lecture. Now, if I have P implies to Q is the same as not Q implies to not P. Or if I have P or Q is the same as not P implies to Q. So constructing a new logical equivalency. Yes, here we say that we can show that 2 expressions are logically equivalent by developing a series of logical equivalent statements. So to prove that A is the same as B, we have here 3 straight lines. A is the same as B. We can produce a series of equivalences beginning with A, then we end with B. Now they say we should keep in mind that whenever a proposition which is represented by propositional variables occurs in equivalences listed earlier, this may be replaced by an arbitrary complex compound proposition. So let's see an example now. Here is equivalency proofs. We want to prove that P or not P and Q parentheses or invert or negate is logically equivalent to not P and not Q. So we can see that the first expression is more complex, have more terms than the second expression or more operators. So I'm going to use the first expression to solve it, and I'll see if I will arrive at the answer of not P and not Q. If we arrive at this answer, that means the both expressions, or in this case, propositional expressions, are the same or they're equivalent. So we write down the complex expression here. P or not P and Q parentheses or invert, again, is the same as writing. Remember, we want to remove the not the invert in the front of the parentheses, the outer parentheses first before the inner parentheses. So we use the second DeMorgan law, which means we are going to invert everything, 2 things, not P, so this time or become N, then invert of not P and Q. And that's what we have here. Next, we can invert the inner parentheses. So it will be invert P. Now we have N, so it will change to O, then not Q. So invert P will cancel, the invert will cancel each other. So we get not P and P or not Q. Here we can use the distribution now. So we say not P and P or not P and not Q. Then we can rearrange this because we can say not P and not P. I mean, not P and not Q, and also the same thing, P and Q. So we can arrange not P and P to be together. So here we get not P and not P will give me F. Not P and P will give me F always. Because if P is 1, 1 and 0 is 0. 0 and 1 also is 0. So not P and P give me F. Then I have not P and not Q. And here what I did, I just do commutative law, exchange the position. So NP and not P and not Q or F. Using the identity law, if I have P or F, the answer will be P. So here we have not P and not Q, which again is the same. That's what we want to do. So this means the first expression here, P or not P and not Q parentheses or invert is the same as not P and not Q. They are the same. So this is another example. We have P and Q in price to P or Q. Now we want to prove that this is true. True means the tautology. So based on the truth table, we can get not P and Q or P or Q. So removing the parentheses, I get N, not P, N becomes O in the second line. Then we get Q. Then we get or P or Q. So we convert it, not P or P, then not Q or Q. So this becomes T or T, and the answer will be T. So this is tautology. Always this expression is true. So let's solve some few problems here. This is a question from our course textbook, exercise 2, section 1.3. They say we should show that not P and P are logically equivalent. So these are two cases. If P is true, then not P is the negation of the false proposition. So that also will be true. Because if P is true, not P will be false. And then not false will be true. So that's why we say if P is true, then not P will be not false. And not false also is true. So we say similarly, if P is false, then not P is also false. Because we are going to, if P is false, not P will be true. So not true will be false. Therefore, the two propositions are logically equivalent. Because if P is true, not P will be not false, and not false is the same as true. Second example, they say use the truth table to verify the first DeMorgan law. So they already given us the expression. We have P and Q all invert. DeMorgan law said it to be not P, N will be O, then not Q. So this is DeMorgan first law. Now, to prove this, first I will look at the expression. Using truth table, I will look at the expression. How many inputs I have or variables? I have 2, P and Q. So the possible combination will be 4. So I start with the PQ. We have TT, TF, FT, FF, so that's 4. Next, I have P and Q in my expression, so I'll look for P and Q. So P and Q, we are going to get only one true. So true is true. The rest throughout is false. Then if I know P and Q, then not P and Q will be opposite. So if it's T, it's F. If it's FT, FT, FT. Then we have not P or not Q. So I look for not P. P is true, so not P is false. Another true, false. P is false, so not P is true. P is false, not P is true. Then I look for not Q. So Q is true, is false. False is true is false, false is true. So now I have to look for the expression not P or not Q. And they are here, so the only time I'll get false is when both are false. So not P is false, not Q is false, so it's false. Now false true will be true, true false will be true, true true will be true. So now let's look at the two terms, their output. P and Q or invert is FTTT. And not P or not Q is also the same, FTTT. So this means the answer will be true. They are the same. Now the next question says we should use DeMorgans laws to find the negation of each of the following statements. So here I have Kwame will take a job in industry or go to graduate school. So negation means opposite. So this means if Kwame will take a job in industry, then Kwame will not take a job in industry. Or go to graduate school means or not going to graduate school. So let's see the answer. Kwame will not take a job in industry and will not go to graduate school because it's negate, to negate. DeMorgans again deal with the negation of an expression or variables. So Yoshiko knows Java and calculus. So that to negate this means Yoshiko does not or do not know Java and calculus. So here we say Yoshiko does not know Java or does not know calculus. James is young and strong. To negate this, it means James is old and weak. So James is not strong, and also James is not young. Rita will move to Oregon or Washington. To negate it means Rita will not move to Oregon or Washington. So Rita will not move to Oregon or will not move to Washington. Question number 10 or exercise 10, section 1.3. They say for each of these compound propositions, use the conditional disjoint equivalency, which we saw in our slides example 3, to find an equivalent compound proposition that does not involve conditionals. So we have not P implies to not Q. And they say again, for each of these, we should use conditional disjunction equivalence to find an equivalent compound proposition that does not involve conditionals. So here we say we can apply the equivalence P implies to Q equal to not P or Q to the conditionals in original statements. So we have not P implies to not Q is the same as P or not Q. Now we have P or Q implies to not P. This means we can use the conditional disjoint equivalence. We can write this as not P or Q or not P, which will give us not P. This is all, so it will be N and not Q or not P using the second DeMorgan Then now we have P and not Q or not P. So by using the absorption, this will give us not P. Now the C said we should have P implies to not Q, and then implies to not P implies to Q. So here we get P implies to not Q, which implies to not P and Q. So this is same as writing not P implies to not Q. Instead of using implies, we use or, not P implies to Q. Then we use our rules here. So here is the same as writing not P or not Q. Not P or not Q. Or not P or Q. So this will give me P, and this will be N, and this will be Q. And N, not P will be P and Q. So we get P and Q or P or Q. And that will give us P or Q. Okay, so this will be the conclusion of our lectures on propositional equivalency. Again, we will continue with the part 2 of it in our, again, next lectures. Again, thank you for your time. Thank you. Also, I'm going to post this lecture in YouTube. So if you have any comment, we'll be glad to listen, or you can like, and also you can subscribe, so that if I post any new lectures in computer science or mathematics, you may get notified.